Hello everyone, in this presentation I will discuss our work that focuses on exploiting inter-annotator agreement to improve classification in the presence of noisy labels. In many supervised learning tasks, it is common practice to ask human evaluators to annotate the training data in order to assign to each sample multiple labels. This can be done also through an automatic labeling process. This is done precisely because the annotators can make mistakes, and indeed in practical settings significant disagreement among the annotators is often observed. And this paper focuses precisely on this scenario of supervised learning with multiple annotators providing potentially noisy labels. In this work we analyze the case of instance-independent noise, meaning that the probability of annotator mislabeling a sample depends only on the class of that sample. In general, the noise can be modeled throughout the noise transition matrix that we denote by T, and the element ij of this matrix denote the probability that an annotator assigned class J to a sample that originally belonged to class I. We made several assumptions on the type of noise and on the settings. I will invite the interest viewer to check them on the paper. And in this work we exploit this quantity, the inter-annotator agreement, that is defined basically as joint distribution on the label assigned by the annotators, to estimate the noise transition matrix. Indeed, the two quantities are related to each other throughout the following proposition, where here D is the class distribution, so the prior and the classes. So we can exploit the following lemma that expresses T as a function of M and D in the following way. So we can first obtain an estimate of M, for instance in this way, so just by counting the frequencies of two annotators giving the same labels or different label to the same sample. And then once we have an estimate of M, we can estimate T through the lemma. Again, I'm skipping some details and I invite you to check them on the paper. We will be able to provide an error bound on this estimation error. In particular, the error bound depends on the minimum eigenvalue of the estimated T. And then as dependent as 1 over square root of the number of samples. This is also highlighted in the experimental results. Both depends on the number of samples and the fact that for lower level of noise the error in the estimation is lower. Once we have the estimation of T, we can leverage it to compute the posterior distribution of the labels, given all the labels given by the annotators, and use this in two possible ways, either as soft labels, so in the loss, or to weight the samples in the loss. We actually compare the usage of posteriors as soft labels with other aggregation methods, such as majority voting, averaging all the labels given by the annotators, or just picking one at random, on two different datasets, a synthetic dataset, and on Cipher10N, there is a real dataset containing noise. Notice that in this second dataset, the assumption we made on T may not be satisfied, and indeed are not satisfied. However, the method is still applicable and with positive results. In conclusion, we provide a methodology to estimate label noise distribution using inter-annotator agreement statistics. We also show how one can leverage this estimated noise transition matrix to learn from datasets containing noisy labels. We also have some theoretical results on the generalization bounds for backward and forward loss that are two types of noise robust loss based on the inter-annotator agreement statistics. I invite you to check them directly on the paper for more details. Thank you for listening.